Today we are going to see the design of a particular processing unit inside your CPU. The unit that will perform 2's complement, addition and subtraction. We will design the entire unit. Okay, we will go through the design of the entire unit for the CPU A to Z. Okay, so the process of logic design is a complex undertaking. The data processor part may be general purpose processing unit. Look at the picture. This is the control logic. This control logic will control the entire operation of your system. Look at over here. Control logic may have the external input. Okay. Control logic will get the status condition from the data processor, and control logic will send signals to initiate the micro operation. Basically, control logic is responsible to control all the activity inside the CPU. Now, when this control logic sends the control signal or initiate micro operation, the data processor performs the data operation to perform the job. Okay, so it takes the data, input data, and produce the output data. So there are several ways we can design this control unit. Okay, our main focus will see how we design the control unit inside the CPU that control the operation. That's our main goal. Okay, that's our main goal. How to design the control unit. There are several ways you can design the control unit. Look at over here. One flip-flop per state method, sequence register and decoder method, PLA control, microprogram control. Our main focus over here is the microprogram control unit. This is our main focus. Okay. The first method must use SSI, small scale integrated circuit, and MSI, medium scale integration circuit for the implementation. PLA or microprogram which uses the LSI device. Okay, large scale integrated device. Okay. So our main focus again is the microprogram control unit. In the microprogram control unit, what basically it does? How you implement the microprogram control unit? If you recall the last class, in the last class we have written micro instruction for different operation. We have seen how to write the micro instruction to perform different activity. For example, R1 minus R2. Okay, R1 minus R2, you save the result in the register R1. Okay, then you take input data, you output data. Those are the micro operations that we have seen in the last theory class. Okay, so in microprogram control unit, what you do? You write, you combine several micro instructions like that to write a microprogram to perform a specific job. So what is the concept over here? You combine several micro instructions in a particular sequence to perform a particular activity. So that particular sequence of a group of micro instruction is called microprogram. So what we are going to do over here? We are going to write microprogram. This microprogram will be executed by the control unit to output the control signal. Okay, so you write microprogram to generate the control signal. What is the advantage? If you write the microprogram to generate the control signal, the design of the control unit becomes cheaper. Okay, because you don't need to design separate hardware for separate operation for separate instruction. You just implement the hardware for the micro instruction, basic operation, then you combine several micro instruction in a particular sequence to perform a particular activity. That's the microprogram. And you store the microprogram in a memory inside the CPU. Okay, you store the microprogram in ROM inside the CPU or programmable ROM. Okay, several ways you can do. It can be a permanent ROM, you store the microprogram, or it can be programmable ROM. That means you can change or erase the program and modify the program in future. Okay? So that's the advantage of my microprogram control unit. It is cheaper method. For a particular instruction, you write a separate microprogram and instead of the microprogram, you set the specific control unit in an area called control memory. Okay, and you can design large number of instructions because it only takes extra space in the memory, not extra hardware. So it is a cheaper method and lots of instruction you can design. Okay, another design is called hardware implementation. That's costly method. You don't write microprogram over there. You directly design the hardware for every instruction. So size of the hardware become larger, cost go high, and less number of instruction you can implement. Okay. So our focus over here, you will see microprogram control unit. So this is the block diagram of the microprogram control unit. Look at over here, 3 main block. First block, next address generator. So why we need the next address generator? Because you write a microprogram and you store the microprogram in a control memory. So you need to access every line of the microprogram. Okay, there can be microprogram can be sequential logic. Microprogram can be, there are 3 logic you can use when you write a program. What are the 3 logic? First logic is the sequential logic. That means you execute the program line by line, one after other. Okay, first line, second line, third line, sequential logic. Another logic can be selection logic. That means you employ a condition. Based on the condition, you decide whether you will execute the second line or whether you will jump to another location inside the program, okay, or whether you will terminate, okay, based on the condition. That is the selection logic. What is the third logic? Iteration logic. Loop. Okay, let's say 10 times you will execute a particular sequence of micro instruction again and again. Okay, loop operation. So sequential logic, selection logic, iteration logic. So in a program, when you write a microprogram and store the microprogram in the control memory, there can be 3 logic like this. So you need a particular device called next address generator, similar to instruction pointer or program counter of a CPU. What is the job of a program counter? Inside the CPU, an instruction pointer, it holds the address of next instruction to be executed, right? So similar things over here. Inside the microprogram control unit, there is a block called next address generator. The purpose of this block, it will generate the next address inside the microprogram. Okay, the design of this next address generator is the most complex one. For your algorithm, if you can design the next address generator, the rest of the 2 blocks are pretty simple and straightforward. Look at over here. What is the second block? Control address register. It is just a simple register. You can easily design a register by using D flip-flop. Okay, a register. Okay, register is a temporary memory, and by using D flip-flop, you can design a register. Very simple design. Third block, control memory. Just a ROM. You can design the ROM. Okay, the device course, you have learned how to design the ROM, how to design the register. So second block and third block is pretty simple to implement and design. Only complex part is the first block. That's our challenge. So for any given problem, like our main problem over here, we are going to design 2's complement, addition and subtraction. For this problem, we are going to design this block. If we can design the first block for this problem, the rest of the part is pretty simple. So our main focus will understand how to design this first block. Okay, how to design this first block. So look at over here. The purpose of the control unit is to initiate a series of sequential steps of micro operation. A control unit whose control variables are stored in a memory is called microprogrammed control unit. Each control word of memory is called a micro instruction. Look at over here. Every line or every control word is a micro instruction. Okay. A sequence of micro instruction is called a microprogram. Now, there's another technique, just to have mentioned that hardware technique. In the hardware technique, we don't write the microprogram like this. We don't write the microprogram. We don't need this next address generator. We don't need the control address registry. Instead of this 3 block, what is over there? A pure hardware design. For every instruction, there will be a pure hardware design. Okay, completely hardware, no programming. That's the hardware control unit. So the design of hardware control unit is carried out in 5 consecutive steps. The problem is stated, an initial equipment configuration is assumed, an algorithm is formulated, the data process part is specified, the control logic is designed by hardware. Pure hardware design, no programming. Okay. So let's come back to our problem statement. Addition and subtraction of binary fixed point numbers when negative numbers are in 2's complement form. That means 2's complement, addition and subtraction. Now, before we understand the algorithm, before we go to the algorithm, we need to understand how this addition and subtraction works. Okay. The addition of 2 numbers stored in registers of finite length may result in a sum that exceeds the storage capacity of the register by 1 bit. So when you are doing the addition, it may happen that there can be an overflow. And we need to understand when overflow occurs. We have analyzed 2 scenarios over here. Let's say first number is the word A, second number is the word B. And there are 2 scenarios. A less than B, one scenario, another scenario is A greater than or equal to B. So what happens? When A less than B, look at over here. 6 is less than 9, minus 6 is less than 9. So A less than B. So when you do the addition, in that case, what happens? No overflow. Look at over here. Do the addition. Look at the overflow bit. No overflow, 0. No overflow. This is 0. This is 0. No overflow. But when A is greater than or equal to B, perform the addition. Plus 6 minus 9, perform addition. Minus 3. Look at over here. This is the overflow bit. Minus 9 minus 9. A equal to B. So look at over here. When A is equal to B, perform the addition. Look at over here. Minus 9 minus 9. Perform the addition. And we get an overflow. 1. Okay. So this is one case. Keep in mind, when A is less than B, there will be no overflow. And when A is greater than or equal to B, there can be an overflow. This is one scenario we have analyzed. Another several scenario we will analyze. Okay, look at what here. We'll come over here later. Another scenario is over here. 8 different conditions to consider for addition and subtraction. Look at what here. What are the 8 different conditions? Plus A plus B. Addition. When you do the addition, the common sign becomes the common sign of both. You see, A plus B. But when you do the subtraction, look at it. When A is greater than B, when A is greater than B, the common sign becomes the signs of A. You see, for plus A and plus minus B for this one. Okay, for the second case. Okay, we are considering the second case. We need to understand this operation. Okay, to design the algorithm. When plus A and plus minus B, second scenario. Okay, So when A greater than B, the common sign will be sign of A. Common sign of A. Then A minus B. Okay. When A less than B, that means B is greater than A. Then what will be the common sign? Sign of the larger one. Sign of the larger one. Okay. So it comes over here, B minus A. Now, when A is equal to B, what will be the common sign? A equal to B. A equal to B, they're equal. Okay. Just take the sign of A minus B. Okay. Just take the sign of A. Common sign. Just take the sign of A. So three scenario when you do the subtraction. Okay. Third case, minus A plus B. Minus A plus B. A greater than B. Common sign will be the larger one. This A is larger one, so common sign will be negative. Then A minus B. First scenario. Second scenario, when A less than B. B is larger. Okay. B has the positive sign. So common sign will be the positive. B minus A. Third scenario. A equal to B. Just take the sign, positive sign, because they are equal. And then A equal to B. Okay. This one. A minus B. Because they are equal. Okay. When A equal to B, they are equal. Okay. And when you do the subtraction, just take the positive sign, because result comes 0 over here, right? When A equal to B, and if you do subtract, result comes 0. Just take the positive sign, A minus B. Okay. Fourth scenario. Okay. Minus A plus minus B. Minus A plus minus B. So when do the addition, take the common sign A plus B. Okay. And when do the subtraction, look at over here. When do the subtraction, then I think we don't need to worry about, because when do the subtraction, this becomes, okay, there is no subtraction over here, because we are doing the addition. Okay. There is no other situation over here, only one scenario. So I think fifth case, this case, plus A minus plus B. Okay. So you are doing the subtraction over here. So when you are doing the subtraction over here, three scenario, A greater than B. Okay. So take the common sign, because A greater than B, and A minus B. When A less than B, take the sign of B, because B is greater, B minus A. When they are equal, just A minus B. Take the sign plus. And when it comes in terms of plus A minus minus B, that means their actual addition operation, plus A plus B. That means, look at the first case, same situation. So plus A plus B, common sign plus B. So minus A minus plus B. So what happens? This is scenario like fourth case. Okay, same like fourth case, take the common sign A plus B. And when it is minus A minus minus B, okay, in that case, depending on the A greater than B, take the sign of A, common sign A minus B. When A less than B, B is greater, take the sign of B, B minus A. And when A is equal to B, just A minus B, take the sign. Okay. So this is the figure for addition and subtraction for sign magnitude number. In language, if I tell this thing in language, so we can write it like this. When the signs of A and B are identical. So let's continue over here. When the signs of A and B are identical, add the two magnitude and attach the sign of A to the result. So we are explaining, or we are putting language to our scenario. When the sign of A and B are different, okay, compare the magnitudes and subtract the smaller number from the larger. Choose the sign of the result to be the same as A if A greater than B, or the complement of sign A if A less than B. Keep in mind, okay, this is our finding. So we will use this finding to write the algorithm. Okay, for equal magnitude, subtract B from A and make the sign of the result, positive sign of the result. Okay, so again, this is the again more explanation of the same scenario. When the signs of A and B are the same, we add the two magnitude and the sign of the result in the same as the common sign. Okay, same thing. When the sign of A and B are not the same, we subtract the smaller number from the larger, and the sign of the result is the sign of the larger number. Already we have explained this scenario. Now is our algorithm flowchart. 2's complement, addition and subtraction. Look at over here. First step we call state T0. State T0, initial state x equal to 1. We take a variable we call, okay, at the initial state a variable x equal to 1. Initial state. Now there are, look at the hardware design. Before we come over here, I think we need to understand this hardware design. This is the equipment configuration. The two signed binary numbers to be added or subtracted contains n bit. The magnitudes of the numbers contain k equal to n minus 1 bits are stored in registers A and B. The signed bits are stored in flip-flop A's and B's. Look at over here. This is the ALU, arithmetic logic unit, we have designed in our first class. It performs 8 arithmetic operation, 4 logic operation. Now, this is the magnitude, register A. This A register holds the magnitude of word A, not the entire word A, just magnitude. This is the B register, it holds the magnitude of word B. Now, this is the sign bit, BS. It holds the sign of the word B, one flip-flop. AS, this AS register holds the sign of word A. And this is the overflow bit. If there is an overflow, this will be set to 1. Otherwise, clear to 0. Now, this is the control logic. Our target, we are going to design this control logic. That's our target. Look at over here. What are the input of the control logic? QA. That means this signal will tell that, okay, perform addition. QS. This signal will tell that, okay, perform subtraction. And X, operation terminated. That means this X will tell that, okay, whether operation has been terminated or not. So this is the control logic. Our focus, we are going to design this. Okay, we are going to design this logic. So what is our algorithm? So this is our analysis we have just gone through. This is our flowchart. Initial state x equal to 1. Now, in the control logic, if you give the signal QS, that means perform subtraction, then how you perform subtraction? First, we take the complement of B, then you perform A plus B bar plus 1, A minus B. You see, this is certainly will be a bar. Okay, that means actually you see we are doing the bar over here. Okay, that means that's come over here. That means A plus B bar plus 1. This is doing the complement, right? Then this is the subtraction. So if the signal is QS, look at over here. If the signal is QS, then we at clock cycle T1 we take the complement of B and then we decide whether we would go to the left side or right side. Okay, that means if the signal is addition, then we don't do the complement. If the signal is subtraction, we do the complement of B. Okay, that means BS to BS. That means sign of B. That means if the sign of B was positive, it will be negative. If the sign of B was negative, it will be the positive. Okay, so we just complement the sign. Okay, because we are subtracting. And if we don't do subtraction, if we do addition, we skip this T1 step. It directly come over here. Now we compare the sign. Two sign, word A and word B. They are equal or not? Okay. How do we compare the sign? Look at over here. If we take exclusive OR gate, this is the sign AS. And this is the sign BS. So when the signs are equal, okay, what happens? Exclusive OR gate, 0, 0, output is 0. 0, 1, when the signs are not equal, output is 1. Okay. When the signs are not equal, output is 1. Otherwise, it is 0. So look at over here. When the signs are not equal, this S become 1. So you will go to the left side. Signs are not equal. You will go to the left side. And when you go to the left side, what algorithm you will follow? Look at over here. This is the algorithm when the signs are not equal. Okay, this is a table to follow the algorithm. And you will go to the left side. That means S equal to 1. And when the signs are equal, S equal to 0. In that case, you will go to the right side. In that case, you will just simply, because equal sign, you will take the common sign and do the addition. Okay, so you just simply perform the addition. A plus B, the result will be stored in A register magnitude, and the carry out, that means if there is an overflow, it will go to the E, and job is done. Come to the initial state. But when the signs are not equal, we perform the subtraction. So how we perform the subtraction? A plus B bar minus 1. Okay, so A plus B bar minus 1, and our arithmetic logic unit can perform this operation, A minus B. We have designed it, right? In arithmetic logic unit, look at over here. How we design A minus B? Look at over here. A minus B. This is A minus B. And this is the control bit. We have to perform A minus B. Okay? So we have our LU can do it. So it performs the subtraction, and the result will be stored in A register, the result. And if there is an overflow, it will go to the E. Okay? That is in step T4, colossal T4. Now, you check the overflow bit. Whether overflow bit is 0 or 1. Do you recall the two scenario over here? Overflow bit will be 0 if A less than B. Okay? And overflow bit will be 1 if A greater than or equal to B. So two situations. So when overflow if E is 0, we check E, overflow bit. That means A less than B. Okay? And if overflow bit is 1, that means A greater than or equal to B. So look at over here. If A less than B, then what algorithm we need to follow? We need to follow this algorithm, A less than B. Okay? A less than B. We need to follow this algorithm. So what we do? What we have done over here? In this case, okay, we take the sign of B. That means we complement the sign of A. When you take the sign of B, that means we are complementing the sign of A. Look at over here. That means common sign is the complement of A. This scenario. Look at the sign. Sign of A was positive. but because of a less than b, it has become common sign is become result of common sign is negative. So we need to complement the sign of a. So that's thing we have done. We complement the sign of a because result a hold the result, a hold the magnitude, and what is the sign of a? Complement because a less than b, right? Then we perform okay a plus 1 okay and okay we perform a bar plus 1 actually a bar plus 1. Look at over here. The 2's complement of a can be done with 1's microoperation a bar plus 1 because a holds the magnitude. Look at over here. Look at the statement over here. Okay, a holds the magnitude. Okay, look at over here. A was negative. So if we take the 2's complement, it becomes positive. 2's complement makes a number, change the sign. Okay, so what we do? We take a bar plus 1. Actually, this is a bar plus 1. This is bar. A bar plus 1. It takes the magnitude. So magnitude we store in the register A, the result of the operation, and we change the sign of A because look at over here. The sign of A get changed. Okay, we change the sign of A. So now our result has the proper value. A is holding the magnitude of the result and it is holding the proper sign. Job is done. You go to the initial state. Okay. Now, if there is an overflow, the situation is A greater than or equal to B. A greater than or equal to B. When A is greater than or equal to B, and you are doing subtraction, can there be an overflow? No, because you are doing subtraction. A greater than or equal to B. So what we do? We clear the overflow bit and go to the initial state. So this is our algorithm of 2's complement addition and subtraction. Okay. Now, this is called state diagram. This is the flowchart of our algorithm, and this is the state diagram of our algorithm. Okay, state diagram. This is the state diagram. Okay, how we write the state diagram? Look at over here at state T0, initial state. No command, no addition. Okay, there's let's say you stay in the initial state. If there is no command, that means addition command and subtraction command they are 0. No command, so you stay in the initial state T0. Okay. Now, when there is command, let's say q addition, q equal to 1, look at over here. Q equal to 1, you go to the state T2. That means for addition, if you do the addition, then state T0, you directly come to state T2. Okay. From T0, you directly come to state T2 for addition. You directly come to state T2 for addition, q equal to 1. Q equal to 1. So from T0, you come to T2 when you perform the addition. And when you perform the subtraction, then you come to state T1. Qs equal to 1. That means we are doing subtraction. From T2, from T0, you come to T1 for subtraction. And from T1, you come to T2. And from T2, depending on A is equal to 1 or 0. If A is equal to 0, then you go to T3. You perform direct addition and go to the initial state. From T2, you go to T3 when A is equal to 0. Addition is done, you go to the initial state T0. Job is done. Okay. Now, if A is equal to 1, then you perform subtraction. Then you come to state T4. From T4, you come to state T5. From T4, you come to state T5. In T5, there are two scenarios. If E equal to 0, you come tested T6. From T5, you come tested T6. From T6, you go tested T7. Okay. From T6, you go to start T7. From T7, you go to start T0. T5, if equal to 0, you go to start T6. From T6, you go to T7. Then you go to T0. Job is done. And if E equal to 1, from T5, you directly go to T0. If equal to 1. So this is called state diagram. Okay. So you need to learn how to draw the flowchart based on the algorithm and how to draw the state diagram of your algorithm. These are important part of your design. Okay. Next thing, we are going to design our entire system. Let's look closely at the data processor register part. This is the ALU, arithmetic logic unit we have designed in our first two lecture. This is the A register, this is the B register. How to load data to the register by using a signal called LLoad. Okay. This is the signal for S0, S1, S2 carry in for the ALU operation. Mood select pin, function select pin S0, S1 and carry in pin. This is the carry out. Carry out goes to the overflow over here. This is the sign of B. The control signal to change the sign is Y. Y will change the sign of B. The control signal Z will change the sign of A. Okay. So we are going to design. So we are giving name of the control signal for different operation. Like we have given signal Z to change the sign of A. Signal Y will change the sign of B. A will load data to the A register. This carry out. W will take care of overflow bit to write the bit over here. Okay. So the operations between A and B can be done with the ALU. Okay. The operations with AS, BS, and E must be initiated with separate control variable. AS, BS, and E, they must be initiated with separate control variable Y, Z, and W. So we have introduced three new variables over here: Y, Z, and W, and L also. This variable already you know, right? So let's go with the complete design. So this is our complete picture of the control unit block. You see, this is the initial state. So this is the output from the control unit. Okay, X, S2, S1, S0, carry in. So control unit will output this signal. L, load A and E from the ALU. L signal. Okay, L signal, load A and E from the ALU. Overflow bit and the result of ALU. Y, Y will complement the B. Y will complement the B. J will complement the A. Sign. They'll complement sign. W will clear you. W will clear you. Make it 0. So these are the control signal from the control logic for our design. And this control logic will have this input: QA for addition, QS for subtraction, S whether we do addition or subtraction. This will indicate whether this sign AS and BS are equal or not. Okay, if they're different, then S will be 1. If they're equal, S will be 0. Sign. Okay, it compares the sign of two number. This is the E. Okay, what is E? Overflow bit. Okay, so these are the input to the control logic. This is the output. Our job now, we are going to design the circuit for it. We are going to design this circuit for it. Okay, how we design the circuit? Issue from your flowchart and state diagram. Okay, Look at the state diagram and flowchart. Control state diagram. At T0, what you do? At T0, x equal to 1. At T0, x equal to 1. Okay, look at over here. At T0, x equal to 1. At T0. At T1, what you do? You complement the sign. At T2, you do nothing. Done by the hardware. Exclusive OR gate. Over here, it is directly done by the hardware. So no control signal is required over there. So at T2, no control signal. Directly done by the hardware. At T3, what you do? Perform addition and write the overflow bit to the erased. Carry out, go to the erased. At T4, what you do? You perform the 2's complement subtraction, a minus b. This is a minus a plus b by minus b by plus 1. At T4, you do the subtraction. Plus, you send the carry out bit to the erased. The T4. At T5, what you do? At T5, you send 0 to E. At T5, you send 0 to E. Look at over here, you send 0 to E. T5. Okay. Then at T6, what you do? Take complement of the A, then take the magnitude. At T7, you take the magnitude. At T7, you take the magnitude of A. So it goes to the register. A holds the magnitude, and AS register, AS flip-flop holds the sign. And already we have done the explanation of it, right? So these are the control state diagram, okay? And at different clock period, we perform this operation. So if we design a hardware control unit, okay, then our control unit, that means if this block is hardware design, this block will output this, the record signal from here to perform this operation. So how it does? Look at over here. This is our control state, right? At T0, x equal to 1, x equal to 1. Okay, so x equal to 1 at T0, and other signal will be 0. Okay, this is the control signal table. At T1, you need to take complement of the sign of BS. How you can take complement of the sign BS? By sending the signal Y. Y, take the complement of the sign BS. So look at over here, Y equal to 1. Other are 0. At T2, no operation is performed, so all are 0. No control signal is required. AS exclusive or BS done by the hardware. Okay. At T3, this operation A plus B and C out go to the register overflow bit. So what is A plus B? At T3, A plus B. How you do A plus B? Look at over here. This is A plus B. And C out go to the register. C out go to the register. How it does? C out go to the register. Okay, C out go to the register. I think it's over here. Look at over here, A plus B. So how you do A plus B? 0, 0, 1, 0. S2, S1. 0, 0, 1, 0. A plus B. 0, 0, 0, 1, 0. Okay. X equal to 0 at this one, x equal to 0. Now what is a load? This load will load the result to the register L. Load A and E from ALU. That means L will load this addition result to the register and C out from the LU to E. Look at over here. L does two jobs. It loads the register plus C out from the LU. Okay. So L should be 1. Okay, job is done, other signals are 0. And at T4, A minus B. What is A minus B? Look at over here. A minus B. 0, 1, 0, 1. 0, 1, 0, 1. Okay. And how to load the result? L equal to 1. All other signals are 0. Then at T5, 0 to E. How is perform 0 to E? Look at over here. Clear E. W. W will clear the E. Okay. So W equal to 1. At T6, 1's complement. 1's complement. Okay. How we do the 1's complement? A bar. Look at over here. A bar. 1, 1, 1. Sin, don't care. You have given 0, okay? Sin, don't care. 1, 1. This is 1, 1, 1. Okay. And how you load the result? L. L will load the result to A. L. Okay. And finally, 37, A plus 1. Okay. You may have a question. Why are you doing twice time? Let's say, why not A bar plus 1 in a single step? Look, if you look at over here, our table, ALU table, there is no operation A bar plus 1. So we do in 2 steps. We take the magnitude in 2 steps. First, we just take 1's complement, then we add 1. So we do 2-step operation to get the magnitude. Okay. Since we don't have a single operation A bar plus 1. So first we do A bar, then we take A plus 1. So what is A plus 1? 0, 0, 0, 1. So 0 and load L equal to 1 and load the sign. Okay. This L equal to 1 will load A. And how to change the sign of S? By using the signal. Look at over here. Change the sign of S. Z. Z. Complement of sign S. So Z equal to 1. So this is our control signal table. Now apply the knowledge of logic design, digital logic design. Write the equation for the signal X. Write the equation for the signal S2. Write the signal for S1, S0, Sin, L, Y, Z, and W. Draw the design the hardware. So what is the signal of X? You will generate the signal X at clock cycle T0 all the time. If the clock cycle T0, generate signal X. So what is the equation of X? X equal to T0. Very simple. You are designing the hardware. What is the equation of logic equation of S2? You generate S2 only when clock cycle is T6. So logic equation of signal S2 is T6. What is the logic equation of signal S1? Look at over here. T4, or if the cycle is T6, you generate T4 or T6. So similar way, you write the equation of all the control signal and just design the hardware. This is your logic equation, design the hardware. Job is done. This is the hardware control unit. Okay, this is the Boolean function for control unit. That means this is the block. You will put the hardware over here in the control logic. So this hardware will get the input signal, produce the output signal to perform operation. This is the hardware control unit design. Okay, no programming. So next we are going to see how to design the microprogram control unit. So this is the hardware control unit design. Okay, this is our hardware. Next we see microprogram control unit design. In the microprogram control unit design, what is our main challenge? Design the first block. Next, address generator. So how we design the first block? Look at over here. This is the hardware configuration for the first block. Okay, don't get afraid. Okay, just let's analyze carefully. You'll be able to understand it very easily. Okay, look at over here. First thing, the hardware will design of the first block of the microprogram control unit. It will design whether the operation is subtraction or addition. Depending on the required operation, it will load the address of corresponding micro operation. Look at over here. This is our micro program algorithm. We have already designed the flowchart. We have done the state diagram. This is in the language form. Okay, look at over here. At clock cycle T0, x equal to 1. If Qs equal to 1, then go to 1. And if Qa equal to 1, then go to 2. Cycle 2. If the sign, that means if there is no request of addition and subtraction, that means no request, then go to 0. That means stay at T0. Okay, this is the statement for state or cycle T0. Okay, so what basically you do over here at state T0, if there is a need for operation, you load the corresponding address of T1 or T2. Okay, what is the address of T1? At T1, what you do, you just complement the sign. After complementing the sign, that means you need to perform the subtraction operation. That means Qs equal to 1, start subtraction. And if you go to the step T2, at step T2, what you do? Look at the flowchart over here. At step T2, what you do? You compare the sign of A and B. Okay, if the sign is equal to 1, then go to T4. That means go to the subtraction. And if the sign go to T4, that means from T2 you go to T4 directly if the sign is equal to 1. And if the sign is equal to 0, then perform addition, save the carry out bit in the E register, go to 0. Job is done. Okay. Now, if you come to step T4, then from T4 you go to T5 equal to 1. Okay. If equal to 1, then make equal to 0 and job is done. And if E is not equal to 1, then complement A and step T6 and A plus 1 to get the magnitude, store the magnitude in A, complement the sign, okay, and go to 0. Okay, so this is our language form of our symbolic. This is called symbolic microprogram. Now we need to translate this symbolic microprogram to machine language like this. Okay, look at over here. This every line of the microprogram is called a micro instruction. Micro instruction has 3 parts. This is the control signal part, control word. This part is called control word. Okay, control word. Control word. Okay, control word. This control word part already we have designed from here. Already we have explained how to design this control word. Simply this step. These are the control word. Now with this control word, you need more information for the microprogram control unit. Look at over here. For this control word, how you go to step T0, T3 and T4. So there will be address part. Whether you will go to you'll stay at T0 or whether you will load the word step 1 or 2, that depends on the control word. Okay, if the control word has the additional instruction, then you will go to 2. If the control word that means has the instruction for subtraction, you'll go to 1, right? So how you do it? So there are two other part we need. One called is the address part. This part is the address part. So we divide internal control microprogram control. I think what microprogram instruction. This is called microprogram instruction. Micro instruction has 3 parts. One part is the control word part. Other part is the address part. Okay, and how you select the address? So this is the address part, and this is the address selection bit. Okay, so 3 part: control word, address part, and address selection bit. How you select the address? Whether you will stay over here or whether you will go to another location. How you select the address? So address select bit. So look at the design. Bit number 13, 14 is the address select bit. Bit number 10, 11, 12 is the address bit. And these are the control word. So look at the diagram over here. So if the control word is QS, that means if the signal is QS, then you load this address 001. That means do the subtraction. This is the address of subtraction. That means from step 0 you'll go to step 1, T1. This is the T1. So address of T1 should be loaded in the control address register. So that you go to step T1. You see, this is the control address register. This register will have the address T1. If the signal is addition, okay, if the signal is addition, this will have the address 001, T1, address of T1. You see, this is the address of T1. 001, address of T1. Okay, so if the signal is QS, then address T1 will get loaded in the control address register, and you will access the ROM and go to that particular line of your program. Look at over here. This is the particular line of your program, T1. T1. You come over here. If the TS equal to 1, you come to T1. So how you come to T1? You see, this is the selection bit 01. 01. 01 tells that you see this 01. This is the selection bit 01. Select bit 13, 14. This 01 will tell that load input to control address register. That means load this is the input, load it to the control address register. So that you can come to T1, second line. Okay. And if the signal is QA, you come to T2. Look at over here. You come to T2. So if the signal is QA, addition 010, T2 will be loaded over here. So load 01. Your bit position 13, 14, there will be 01. Look at over here. This control bit will be 01. So this will load the address of QA or T1 or T2 based on the signal over here. And if they are both 0, stay over here. So this will decide, this the select bit will decide whether you come to T1 or T2. So this entire line is called first microprogram instruction. This is the ROM address. At this address, you store this particular entire line. Okay, three part. This entire three part, control word, address part, and address select part bit, they make a single micro instruction. So one micro instruction we have stored at location 0. Second location is to the second micro instruction that will perform the, look at over here, complement of the S. And after this, you need to go to the line T4. No, from the 0, 1, you go to 1 to 4. How you go to 4? Look at over here. This is address part. You see, 1, 0, 0. From I think 0, 1. From here, same place you go to 0, 1, 0, 2. From 1, you come to 2. Okay, from 1, you come to 2. Select bit select part is 0, 1. Load the address. From 2, you come to 4. Okay, if S equal to 1. Okay, you come to 4. So you write it like this. This is 2. Okay, at 2, this is the control word. No control signal done by the hardware. Compare AS and PS. So all are 0. So from here, you come to 4. Why you come to 4? 1, 0. If the operation is QS, that means you see S equal to 1, then go to 4 directly. If S equal to 1, go to 4 directly. So address is already given in line 3. In line 3, in line 2, address is given, okay? 0, 1, 2. In line 2, address is directly given. From 2, will come to 4. Address is given. And how you load the address? 1, 0. You see, look at over here, your design. When there 1, 0, what you do? Load input to control address register if S equal to 1, and increment control address register if S equal to 0. Look at over here. You load the address 4 if S equal to 1. That means sign not defined. And in increment, that means you will not go to the address 4, you will come to address 3. From 2, you will go to 3. So when S equal to 0. So this is the selection bit for it. So look at over here, 1, 0. 1, 0 is the selection bit. So whether you will go to 3 or 4, that will determine the selection bit, depending on the S. So this is the way you write every line. That means you just translate this language form in machine language like this. And this is the hardware design. So look at the hardware design. This is the operation of this multiplexer, whether I think 13, 14, okay? How to load or increment. Whether you will increment or whether you load the input in your instruction to the controller register, that will determine by 13 and 14, bit 13 and 14. Okay, so what we see over here finally, every line is a micro instruction. A micro has 3 main parts. One part is the control word, other part is called address part. That means if the condition is satisfied, then you go to that address. If the condition is not satisfied, you don't jump to that address. You simply can increment, go to the next line. Okay, so this is the scenario over here. This is the way you write your microprogram. So every line is a micro instruction, is 3 parts: address control word, address part, and selection part. If the condition is true, then you jump to the address given. If the condition is false, then you stay. You don't go. You don't jump. You stay on the. Go to the next line. Just increment. So this is the hardware design. Either you load the address to jump, or you simply increment. The condition is false. So this is a complete design of your control unit. This is the circuit. Over here, you store your microprogram. That means you store this complete microprogram, entire microprogram. Microprogram has three parts: control word, address, and controls address selection bit. Okay, condition bit. So this every line is a micro instruction. This so entire program. This is the entire program. This is your entire program. This is your entire program. This entire program get stored over here inside the ROM. This is a micro program, and you have designed this hardware. Okay, this hardware. This is a hardware design that will implement this logic. Okay, whether you go to the next line, whether you jump to another address, whether you go to on the same location, job is done or not. Okay, performed by this logic, control logic. So this is the microprogram control unit design. Okay, initially it looks like complex, but once you practice, keep in mind every line of a microprogram is called a micro instruction. Micro instruction has three main parts: control bit, control what? That will control the operation that will be output. That means this control word. This is the control word. It will get outputted from this control logic. Operation will get performed. And how this control word will be outputted, at what line of the micro program you will go, or it's on the same line, or just go to the next line, that will determine by this logic. And this is the mark selection bit. Whether you will, this is the control bit actually, bit position 30 and 40. This control bit will instruct whether you will jump to an address, that means whether you load the input or whether you will increment, go to the next line, or whether the job is done. Okay, you see. So this is the address selection bit or condition bit. Okay, depending on the condition bit, your program sequence get controlled. Okay, the program sequence get controlled. So this is the way you write your microprogram. The main advantage, once you write the microprogram and you store in the ROM inside your control unit, it does the same job like hardware design. But advantage, you can store many microprogram inside the ROM. Okay, many microprogram. So lots or different number of instructions you can design. Many instructions you can design. But if you do the hardware design like this, no programming. For every algorithm, like this hardware for 2's complement addition and subtraction, one set of hardware. For another operation, another set of hardware. For another operation, another set of hardware. So what it takes? Your hardware design will be very complex and large. Cost will go very high. And once you implement the hardware, you cannot change it. This is a hardware design. But in microprogram, you simply write a program like this. Okay, this is your program. And you can easily change the program in the future. If you store your program inside a memory that is reprogrammable, let's say a programmable ROM, then you can update your program in the future. Okay, and many instructions you can design. That's the advantage of microprogram controlling. You can modify many instructions you can design, but operation become little bit slow. Speed goes slow because look at the many operation. And in hardware design, it is combinational logic circuit. Get input, produce the output. Faster operation. So if you want to do the faster operation, go for the hardware design. But if you want the flexibility, manual instruction, but you can have some more time, go for the microprogram control unit. Okay. In microprogram control unit, you can also modify your design. The concept of modifying the program in future is called dynamic microprogramming. So that's the end of the class for today. Any question?